So here's question number 6 from the 2012 BC exam. And in this problem, they give you a function g. They tell you it has derivatives of all orders. And then they tell you what the Maclaurin series representation for g is. So here would be the general term in sigma notation. And then here would be the first few pieces of expanded form for that series. What we're asked to do in part A is we're asked to use the ratio test to figure out what the interval of convergence for the Maclaurin series is. So the ratio test is going to require you to check the limit of this ratio. You're going to generate the a sub n plus 1 term by putting n plus 1 here, and as well as here in the general term for the series. You will notice that I haven't accounted for the -1 to the n plus 1 within my limit here. And the reason for that is because of the absolute values. The absolute value of -1 to the n, -1 to the n plus 1 is just going to be +1. So it's just going to kind of clutter our work if we include that within our ratio test here. So that's why you see that omitted. But I have put n plus 1 in place of this n. The one thing that's kind of tricky that I see people overlook from time to time is they just kind of think in their head, all right, n plus 1, that means this power is going to go up by 1. So they write 2n plus 2. They just kind of add 1 to this power. But you're literally putting n plus 1 in place of this n. So if you look at it like this, it should be pretty obvious that you're going to have to distribute in to make that have the proper value within the ratio test here. So you will see that I did distribute in 2n plus 2 plus 1 got me 2n plus 3 as the new power on that x. Similarly, in this denominator, I put n plus 1 right here. I didn't just add 1 to this and make it 2n plus 4. I'm putting n plus 1 in place of n. So if you distribute here and then you add your 3, you get 2n plus 5 in that denominator. And then here is just the reciprocal of a sub n. And again, the -1 to the n piece is omitted because of the absolute values. And then you have to think about how this is going to simplify. So we should have a lot of cancellation occur here. What we have in this numerator right here is we have 2n plus 3 factors of x. In this denominator, we have 2n plus 1 factors of x. There are 2 extra factors of x in this numerator that are not present in this denominator. And so if you use division of like bases, you're going to subtract this power from this power. That's going to give you an exponent of 2 on your x. Now, I have also factored that outside of the limit because once this is an x squared, if I cancel this with all of these and this new exponent becomes a 2, x squared is unaffected as n approaches infinity. So now within the limit as n approaches a certain value, that can be removed. So that's now out in front of the limit. Something that's tempting to do would be to cancel these 2 n's, but you can't do that because you're going to violate the order of operations. You've got a set of grouping symbols here, got a set of grouping symbols there. You can't dip inside those parentheses and cancel those 2 n's. So within the limit, you're left with 2n plus 3 over 2n plus 5. Now, you do get infinity over infinity initially for this limit, but if you use L'Hopital's rule, you're going to get 2 over 2. And so this limit's going to have a value of 1. And so your result is going to be the absolute value of x, which is factored out, times 1. You want to figure out when that result is going to be less than 1. So the absolute values being applied to x squared get kind of redundant, right? Squaring a positive or a negative makes it positive. Taking the absolute values of something just makes it positive. So I kind of dropped the absolute values when I went from this line to this line. And so I got x squared needing to be less than 1. And if you solve that, you're going to realize that x has to be between -1 and 1. Now you notice my final answer here. Initially, this answer looked like this. I only knew that I converged when x was between -1 and 1. I did not yet know what happened at these endpoints because the ratio test, which we were using, is inconclusive when your limit equals 1. And if x is -1, if x is +1, look at this result. This result is going to equal 1. And so we're going to have to manually consider what happens when we have the x value at those endpoints being placed into the series. And so when you put 1 in place of the x in the series, that gives you this. 1 to a power is just 1. So really you get this. And if you think about this is very similar to the alternating harmonic series. You could use the alternating series test to show that this series converges. And then if you put -1 in place of the x, You've got multiplication of like bases here, and if you add those powers, you've got 3n plus 1. Now if you think about 3n plus 1, 3 times 1 is 3, plus 1 gives you an even exponent. 3 times 2 is 6, plus 1 gives you an odd exponent. So this is kind of a goofy exponent. We're not used to seeing that exponent occur, but it will cause this to be an alternating series. And so this is really the exact same series as back here, which is also going to cause that series to converge by the alternating series test. Therefore, we do converge at both endpoints, which means we can include -1 and 1 within our interval of convergence. When we move into part B, they tell us that the Maclaurin series evaluated at 1/2 is an alternating series. The terms decrease in absolute value to 0, which basically means it's a convergent alternating series. The approximation for g of 1/2 using the first two non-zero terms is 17 over 120. Show that this approximation is not going to differ from the actual value of g of 1/2 by more than 1 over 200. So I kind of paraphrase the question there. You know, our error, the difference between g of 1/2 and our estimate is going to be smaller than 1/200th. And so what you should know is that when you approximate the value of a convergent alternating series with a partial sum, the estimate is not going to differ from the actual sum of the series by more than the absolute value of the first term that you've omitted from the sum. So if you take the series and put 1/2 in place of the x's, if you're using these first two non-zero pieces, that's what gives you the value of 17 over 120. Now the first term you've omitted is what I have boxed up here, 1/2 to the 5th divided by 7. So the difference between the actual value of g of 1/2 and 17 over 120 is going to be less than the value of this first piece that's been left off. And the value of that first piece that's been left off, if you simplify it, raise 1/2 to the 5th power, and then rather than divide by 7, multiply by the reciprocal, multiply those together, you get 1 over 224. 1 over 224 is smaller than 1/200th, so we do have a maximum possible error that is smaller than the value that they suggested of 1/200th. And then in part C here, they want you to write the first three non-zero terms and the general term in the Maclaurin series for g prime. If you have the Maclaurin series for g right here, g of x is going to converge to that Maclaurin series on the interval of convergence. So if you take this equation and you do the derivative on each side, the derivative on the left gives you g prime, and the derivative on the right here is easy to be intimidated by, but it's actually not too bad. You're just adding a bunch of pieces together. So we can just copy the sigma, copy the sum, right? When we take the derivative of a sum, we can just do the derivative of each piece and add the results. So we're copying the sigma. The thing that's easy to do is get concerned about this piece here, -1 to the n, and this denominator here. We're doing a derivative with respect to x, not with respect to n. This is a constant. So -1 to the n can be copied into our derivative, and then the over 2n plus 3, or the 1 over 2n plus 3, can also be copied into the derivative. So the only thing that we're going to have to do is do the derivative of x to the 2n plus 1. Well, that's just x to a power, so we're going to multiply by the power we started with. We're going to subtract 1 from it, and 2n plus 1 minus 1 gives you 2n. And then we want to write out the first three non-zero terms, and then the general term. Well, the general term is actually right here. We get that right away just by taking our derivative. And if we want to go ahead and apply the index value of 0, the index value of 1, and the index value of 2 to generate the first three non-zero terms, we're just putting 0, 1, and 2 in place of all these n's, and we're simplifying. So that's just, plug and chug, more or less. And if you simplify that expression, you're looking at these for the first three non-zero terms, and then the general term is represented here. I just copied that into my expanded form for that series. And that is number 6 from the 2012 BC exam.